In this problem, the question asks us about throwing a package. We know we're standing on the ground 3 meters from a building. We want to throw the package from our shoulder level to someone who is 4.5 meters above the ground. We're asked at what speed and angle should we throw the package so it just barely clears the windowsill. Let's start with some analysis of this problem. See if you can draw a picture, figure out what kind of problem this is, and do as much analysis as possible. All right, there's quite a lot involved in analysis and planning. And before I get started, I would like to say I copied this wrong. It's 4.2 meters above the ground. All right, so here's my shoulder. Here's the window. I've drawn them 3 meters apart. I forgot to label that 3 meters. And my shoulder is 1.5 meters above the ground. The window is 4.2 meters above the ground. Here it is getting thrown from my shoulder to the window. I've decided this is the start and this is the end. And notice I'm following, in general, the problem solving strategy where I started by making a drawing, including as much information as possible. And once I start making this drawing, I see that it's moving in the X direction and the Y direction under the influence of gravity. So I think this is a 2D kinematics problem. It's always nice to figure out what kind of problem it is. With the goal of the initial velocity, magnitude, and angle, right? At what speed and angle should I throw the package so that it just clears the windowsill? So at what speed should I throw it? That's at the start, so that's the initial velocity. Okay, so there we are. That's my goal. What velocity should I throw it for it to have this motion? I've identified it as 2D kinematics, and I just want to double check. Acceleration must not be changing in time, but it can be a different constant in the X direction and Y direction. And so since this is an object moving near the surface of Earth, this is a classic projectile motion problem, which means that I can approximate it if the air resistance is negligible as 0 acceleration in the X direction and the acceleration of gravity negative 9.8 meters per second in the Y direction. So even though this is sort of at the end of my list, this is the very first thing I figured out so that I would know this is a projectile motion problem. All right, so it's projectile motion. I've made the drawing. I've decided which direction is positive and negative, and I set my coordinate system so that my very beginning position is 0. So that means my initial X and my initial Y are 0. And notice I've set up the kinematics variables, the initial and final positions and velocities in both the X and Y directions separately. And of course, then the thing that unites them is time, which I don't know. All right, then a lot of this one is interpreting things from this from this written description into the variables. All right, so I can decide that my initial position is here, and then I actually know my final position. It's 3 meters over, and that means my final X is 3 meters. And I have to go up whatever 4.2 minus 1.5 is. So if this is my initial X position, this is my final Y position, which is 4.2 minus 1.5. Oops. I still have the 4.5 from before. Let's change that to 4.2 minus 1.5 meters. So that'll be my final Y position. That's up here. Then I have an initial X and Y velocity, which I don't know, and that's my goal. And then, do I know anything about my final X and Y velocity? So there is some implicit information in it just barely clears the windowsill. That means the windowsill is up at the apex of the trajectory. It's just barely clearing it before it would start falling down. And if you remember, the apex is where the Y velocity is 0. So if I throw something up just at the top, when it switches from moving upward to moving downward, it very briefly has a velocity of 0. So I have Vy, my final velocity is 0. So here's what I have. I don't have my initial velocities. That's my goal. I have my final velocity in Y, but not in X. I have my accelerations. I don't have my time. To me, and my goal is to get my initial velocity in X, initial velocity in Y, and then I can put it back together. I guess I could write my plan, right? My plan, use 2D kinematics to get V naught X and V naught Y, and put them back together into a vector. And it looks like, let's see if I have any, either my Y direction or my X direction has only 2 variables missing, because of course that, and I don't need to break my known quantities into X and Y components because we already have that. So we rewrite separately in the X and Y directions. and we solve two separate kinematics equations. So very often I'll solve y to get something I need for x. Well, in y, I do have only two missing variables. I have v naught y and I have the time. So I could use 2D kinematics to find my goal, which is v naught y, but also to find time, which I would then need to find my v naught x. So that'll be my plan. Find v naught y and t from the y direction. So that'll probably be two different of my kinematics equations. Use t from there to find v naught x. All right, so there's my plan. Why don't you pause, see if you can choose the correct kinematics equations and execute this plan. All right, so the first equation I selected was, well, a lot of the equations, in fact, nearly all of them involve time. And since I don't know time and I want to find v naught y, I selected the one equation that doesn't have time here, and then I plugged in the things that were 0 as the next step. This initial velocity in y is the thing we're hoping to find, but the final velocity in y is 0. And then the initial y position is 0, giving me this equation here. Then I subtracted these over to this side and took the square root to get this equation here. And then so once I had that, I plugged in negative 9.8 for this and 2.7 meters for this. Here, notice how I'm keeping my units as I go, and that'll give me meters squared per second squared inside a square root, which is meters per second. And then I'm just keeping some extra significant figures since I'm going to later use this as an intermediate step. When I report my final answer, it looks I should probably have two significant figures because almost everything here has two significant figures, and I'm doing some division. Okay, so now my next thing is to find v naught y, did that, and t from the y direction, because I'm going to need to have t so that I only have two unknowns in the x direction, and then I can find v naught x, which is part of my goal. All right, so why don't you see how much of that part you can now execute? Great, now that I had Vy here, I could really pick any of the other y direction kinematics equations. I happen to pick this one, Vy equals v naught y plus ay t, but maybe you picked a different one. Then because this final is 0, it simplified pretty well. I could do some algebra to get here, plug in my ay of negative 9.8 meters per second squared, the v naught y that I had before to get a time of 0.742 seconds. And again, I'm keeping extra significant figures in my intermediate steps. Once I have the time, again, I have more than one option for what to use for the x direction. Because even though I have a lot of question marks here, since the acceleration in x is 0, v naught x and vx are the same. But I didn't even need to use that assumption in the equation I chose. I chose this one, x equals x naught plus v naught xt plus a half axt squared. This is a 0, and this is a 0, making a very simple equation. Once I have the time, I can solve that for v naught x, and I get this for v naught x and this for v naught y. So now I've followed through with this plan, and then the next step is put these back together to get a vector magnitude and direction. So that's the very last step. Why don't you pause here and see if you can execute to use these two components that we have for v naught y and v naught x to figure out the vector magnitude and direction. All right, I had to make some space to draw my vector, and I always like to draw a head-to-tail addition of the x component and the y component. So here's the x velocity and the y velocity, and then my vector is the one that connects them from the empty tail to the empty head, or the hypotenuse. And this is the angle theta up from the x-axis. Then I have a nice right triangle. I could use Pythagorean theorem to get the length of this part of the triangle, the hypotenuse, and I got 8.3 meters per second because all the units are meters per second here. And then this angle is the angle whose tangent is opposite over adjacent, or the 7.275 over the 4.4, and I got 61 degrees above the x-axis. I could also have found this angle, and if I'd carefully drawn it, that would be another way of indicating the direction that I need to throw the package. And just to practice, I also wrote this in our I hat and j hat notation. All of these n1 should have two significant figures, so I rounded to two significant figures, 4.0 meters per second in the x direction, that's an I hat, and 7.3 meters per second in the y direction, that's a j hat. And so practicing writing this and this as two ways to represent the same vector is another good practice. My units seem to work out. I seem to have something that's up a little more steeply than it is horizontal, 61 degrees, which makes sense because my y velocity was higher. The units all worked out throughout the problem, so overall I think my monitoring is saying this makes sense to me, and I'm done.